So the last thing we're going to look at here is limits at infinity, like it says, and you can see two things that I want to point out. First of all the properties we've learned about limits still apply. So we're not reinventing the wheel here necessarily. We're just looking at a specific type of limits, which specifically are ones that have x or the variable approaching infinity, plus or minus infinity, right? And so um, there are techniques that we can use to solve these ones by hand, but what we're going to look at is the concept of a horizontal asymptote, specifically as it relates to the things down here in this box, which if you had pre-calc with me, we looked at this last semester, for example. You should be familiar with this stuff, in other words, but we're just kind of thinking about it in this new text context of a limit. Okay. Someone say something? I thought I heard something there. No? Okay. So we're thinking about horizontal asymptotes, and we're going to illustrate the idea by thinking about 1 over x. So let's do that. So I'm going to create a couple tables here to evaluate 1 over x, and let's plug some big x values in here, right? Because you can see this limit is approaching infinity, right? And so let's plug some really big numbers into this function. And 1 over x is an easy thing to plug numbers into. You're just dividing by whatever you're dividing 1 by whatever you plug in, right? So let's plug in some big numbers. Let's plug in 100, 1,000, let's do 10,000. And then let's get kind of big, 100,000, right? And we'll do the same thing, but in the negative direction. Well, you can just see because you're dividing by these numbers, the numbers are going to get smaller and smaller and smaller, right? But just to be clear, what we're trying to do here is we're trying to look at the left and the right hand limit. So this one on the left is a limit as x approaches infinity. Sorry, let me redo that. That's approaching negative infinity. So the concept of left and right means like going to all the way to infinity in one direction or the other. Oh, that one's plus infinity though, right? And then the other one is approaching negative infinity. And the numbers just get smaller and smaller, right? Like 0.01, 0.0001, 0.00001. And so the numbers are getting closer and closer to 0. And the same thing would happen in the other direction, but they're just coming up from the negative direction, right? So it's like minus 0.01, minus 0.0001, minus 0.00001. And so one's approaching 0 from the top, you could say like coming down to it, and one's approaching 0 from the bottom, like coming up towards it. And that should make sense because that's exactly what this graph looks like. And we've seen this graph a number of times now, right? There's like a horizontal asymptote right there. We've graphed this, I don't even know, 3 or 4 times already, right? So 1 over x does this. And so we just looked at the outskirts of that, right? We looked at way out here, or way out here, just by looking at the table. But if you look at the graph, don't focus on the middle part because that's not the infinity part, right? When we're approaching infinity, we're like way over here. We're like way out on the edges of it. And so when you look at this in pre-calculus, you talk about horizontal asymptotes, right? You talk about, hey, what happens way out on the edges of graphs? Is it approaching anything way out in the edges? And what we learn in pre-calculus is it happens wherever the denominators are 0, there's a vertical asymptote, right? And then whatever comparison between the degrees and the numerator and denominator, that's what makes the horizontal asymptotes happen out to the side. So basically what we just learned then, let me do this color here. I'm going to write it right here. So based on all this information, the graph, the table, all of that, 1 over x has a horizontal asymptote at y equals 0, excuse me. Right? Because by definition, up at the top there, that's the definition of something being a horizontal asymptote. If the limit approaches something, if the infinite limit approaches something, we have a horizontal asymptote. Right. What do you think? Questions about that at all? You guys remember this from pre-calc? Or is anyone confused about what I'm trying to say with the table thing? All right, so if you recall this back from pre-calc or wherever, it all has to do with the powers, right? The biggest powers control things when you start plugging really big numbers in, right? We're doing infinite limits here, and so we're thinking about plugging in big numbers. And so that's what's sort of being summarized in this box right here. It's talking about what happens in infinite limits, right? So let's say we have some rational function, which just means it's a fraction, right? So this is a fraction right here. And we have a polynomial in the top and a polynomial in the bottom, right? So both the things I'm highlighting right now, we're saying are polynomials. That's the definition of a rational function. And what this tells us, it says something about n and m, right? So let's focus in on n and m. Notice that n and m are in this piece of the definition, right? They're the powers that are in there. It's x raised to the n, x raised to the m. And so what this is telling us in the top here is number one, both the numerator and denominator are going to be polynomials. Hopefully we have a good idea what polynomials are, but now we've been using that term a bunch. And more specifically, the numerator has degree n. In other words, that's the biggest power. And the denominator has degree m. And if you're not familiar with that word from pre-calc, you don't remember that or whatever, this just means the highest power. So you just look at the highest power in the top and the bottom, right? That's all we're saying. As a quick reminder, we're looking at the biggest power in the top and the bottom, because when you plug really big numbers into a polynomial and you raise them to a power, the biggest power is really what's going to matter, right? If you plug, like, let's just look at these examples down here. Let's look at the example on the right here. The biggest power is on the top here is a 5. The biggest top on the bottom here is a 9. If you plug really big numbers into that x and raise it to the 5th power, it's going to be big, right? Think about plugging a million in, right? A million to the 5th is a big number, but a million to the 9th is so much bigger that it's going to cancel out the effects of raising it to the 5th power, is the way to think about that. And the 44x cubed, the 14x, those like don't even matter when you plug something like a million in. The biggest power is what matters. And so just looking ahead, that's one where the bottom and the power in the bottom is bigger than the power in the top, right? 9 is bigger than 5. And so that's this case right here. We'll look at this more carefully, but that's sort of the way to think about this table. All right, confident some folks remember what I'm talking about, but can I clarify anything else specifically before we look at a couple examples? I'll probably just do one. I hope this makes some sense, and then I'll ask you to think about the other couple yourself. Anything at all? I'm trying to remember if I graphed these already. I don't think I did. All right, I'm just going to do this first one, the one I was just talking about. So on this first one, this one right here, we look at the biggest powers, right? We just focus in on x to the 5th and x to the 9th, and we just think the biggest power on the top is 5, the biggest power on the bottom is 9. Since 9 is bigger than 5, or maybe I'll write it in the same way it says up there. It says 5 is less than 9, right? N is less than M. We are in case 2. Right? So case 2, just to be clear, this one tells you what to do if the bottom degree is more than the top degree. And so that's where we are in this particular example. And that one just says, hey, if the top has the bigger or the smaller degree, then the outside limits are going to go to 0. This is just like the example we just looked at. Right? If we kind of go back to 1 over x and we think about what this one looks like, this is case 2 below. Right? The power in the bottom is 1, x to the first. The power in the top is 0, x to the 0. And so this is case 2. And when we looked at the graph, we actually graphed it, we see that it has a horizontal asymptote of 0. So we kind of figured that out looking at the table in the picture. And now we're saying, oh, we didn't really have to do that. We just realized this is case 2 above. And so case 2 tells us that the limit as we approach infinity is going to be the limit as we approach negative infinity, which is going to be 0. So it's going to have a horizontal asymptote of 0. Questions about that at all? And so again, back in pre-calc, or wherever you saw this previously, and if you're in my class last semester, as we talked about this in terms of rational functions, one of the last things we looked at, we were defining it in terms of asymptotes, which is still true, but now we're just saying this is also the same thing as looking at the infinite limit. Right? So it's the exact same thing, just kind of extending the idea to calculus now. Does that seem okay? All right. Gonna see if I can shrink this a little bit. Got a little bit too big on me.
Professor, I just have a kind of like a question.
Yeah.
So basically the first example that we did, the 1 over x,
Yep.
n would technically be 0, right? Because it's 1 to the x to the 0.
Yeah,
then,
that's right. That's
okay.
right. So if we thought about 1 over x, this is obviously x to the first, but this is like 1 times x to the 0, right? Because this equals 1.
Okay. And then the horizontal asymptote would be at y equals 0, like we found.
Exactly. So we're looking
Okay.
at that in this context. N is 0, m is 1, and so n is less than m, and so this is still case 2.
Okay.
Yeah. Good thoughts, sir. Other questions like that? Still trying to make this a little bit smaller. Come on. All right. So yeah, just take a second to think about these other couple. I was going to just let you think about these yourself. If we were in person, I'd probably ask you to group up. I don't think it's really worth doing something like breakout rooms. And so just take a second to think about these. I'm going to maybe draw the pictures as you're thinking about it. I graph these ahead of time, and I'll just sort of start writing things down. But if this makes sense, it should be kind of easy. And if it doesn't, I'd love to hear a question. So maybe start thinking about how this works would be good, right? We're looking at the biggest powers. So in this first one, n is 2, m is 1, right? How does that one work? And the second one, they're the same. Can I do this? Let's see. Oh, I can. I can do it like that, which is what I wanted to do. Cool. I'll throw a couple of pictures on here too. All right, so in that first one, the degree in the numerator is bigger, right? And so love to hear from someone, and I'm going to go ahead and just try to call someone out. Love to hear from maybe Rashid. Are you there, Rashid?
Yeah, I'm here.
What do you think about the first one? We got the degree in the numerator is bigger. Which case is that? What do you think?
So it's 3.
Yeah. And what happens in that case?
Both of them are infinite, I think. So,
Yeah, exactly.
So 0, I think. Y equals 0.
So when it says, so this is case 3, and we're just kind of looking at this part. It's telling us that the limit as x approaches plus or minus infinity is just going to plus or minus infinity. In other words, we don't get a limit because it's not approaching something. It's an infinite limit. In other words, what this is telling us is that the top, because the top has a bigger power, the top grows faster than the bottom. Right? If you think about plugging a million into the function that's on the left here. You would square it in the numerator, but in the bottom, in the denominator, you just leave it the same, right? So a million squared is a big number, but you divide it by a million, and that's less. And every time you plug a bigger number in, the top grows quicker. And so there's no horizontal asymptote is all we can say here. There's no limit, so there's no horizontal asymptote. So the limit as x approaches infinity equals infinity, i.e. no horizontal asymptote. And you can kind of look at the picture and see that, right? If you look out to the right, it's just going to keep getting bigger. And if you look out to the left, it just keeps getting smaller. Not the best picture I've ever drawn, but if you graphed it, you'd see that too.
Is that the case for all problems where the numerator exponent is larger than the smaller one? There's
Yes.
always going to be no horizontal asymptotes for that case.
That's exactly right. Yep. Because the top just keeps getting bigger. So it's not going to approach something. It's just going to get bigger and bigger and bigger and bigger. Other thoughts about that? Well, third case. You there, Jorge? What'd you get in that third one?
Yeah, I'm here.
What's going on in this one? We've got the numerator and the denominator both have the same degree. What case is that?
1.
Yeah, so that's case 1. And what's that one tell us to do? It's kind of weird. Do you know what this notation means?
It's a fraction. The answer is a fraction.
Yep, it's a fraction. What are you dividing? It says an and bm. What are those things?
The exponents.
So notice in this part right here that I'm circling, right? It's those things. So it's saying it's taking the numbers that are in front of the biggest powers and dividing those numbers. And so let me make that note right here. I would suggest making that note. What that says is it tells us to divide the leading coefficients is what that's called. In other words, if we go and look at this example, we're in case 1, right? And so this tells us to divide the leading coefficients. In other words, looking at this problem, when we plug a million into x, we're cubing it in the top and the bottom. So that's going to be the same, right? It's going to be a million cubed on the top. It's going to be a million cubed on the bottom. And so what really matters are the coefficients that are in front of there, the 2 and the 3. Because you'll be multiplying the 2 on the top and the 3 on the bottom. So that's really what's going to control it because you have the same power. And so in this one, we want to divide the 2 and the 3 to get our answer. So this one tells us the limit as x approaches plus or minus infinity is going to be 2 over 3, which is the leading coefficient.
Is there any way you can like zoom into that problem and put them like in the middle?
Is that better?
Yeah, I just couldn't see anything. Thank you.
So that's the leading coefficient in the top divided by the leading coefficient in the bottom. Let me just pause there and see if that seems okay. And so just to be even more clear about that, we want to say this implies there's a horizontal asymptote at y equals 2/3. And that's what I'm trying to show in the picture. What I'm trying to say is this dotted line is at the point 2/3. And so way out on the edges of that graph, it's going to get closer and closer to 2/3. Let me just stop there and see if that seems okay. Actually, I just realized I think I need to put another homework assignment out there. Let me make sure that I'm thinking about this right. Yeah, shoot, there's a homework set called Limits at Infinity that I forgot to assign. So there's going to be, how many are in that one? There are 9 problems in there that are just like this one. Let me just look at them real quick to make sure that it looks good. Yeah. So I'm gonna have to adjust my weekly announcements there to just clarify that there's going to be a second homework due, a second web work. Do that right now. Okay. Questions about anything? Chat looks clear. I
got
put one out there. Yep. Sorry.
I got a question. If you could scroll all the way up, where it says the fact, what does the L stand for again? Is that a limit?
So the question's about this part right here. The L is just if it equals something. So this is just telling us, and let me delete it so I can read it again. This part that I'm highlighting just says, if the limit as we approach infinity equals some number, so this is a y value, or if the limit as we approach negative infinity equals that y value, that's just the definition of having a horizontal asymptote at that point. So you see how, like, get rid of some of this stuff. Like this L and this L are where the horizontal asymptote are. So that's just telling us if we have an infinite limit, that means we have a horizontal asymptote at that point.
Okay, that makes sense.
Or the flip side of that is the definition of having a horizontal asymptote means way out on the edges, the function gets close to that point. Which again is something you see previously in pre-calc or whatever, but we're like relating it to this concept of a limit now. All right, questions about that?
So, for these limits at infinity, these 3 rules are gonna apply to all of these.
All the
Like-
ones that we'll see, yeah, all the ones that we'll see.
All right, good.
We're only going to look at polynomial ones, and if I remember correctly, the ones in the notes are all polynomials. And there's nice applications like this one right here. Let's just look at this quick application. So this is talking about the photosynthetic rate for a soybean plant. And so this is a real function. This function right here, P of I, tells us, so it's how much photosynthesis this plant is doing given a certain light level. Right. So just as a reminder, when lights shine or the sun shines on plants, photosynthesis occurs, which is going to increase as there's more light. Right. So if it's a cloudy day, for example, there's not a whole lot of photosynthesis going on because there's not a lot of light reaching the plants. But as the light increases, you get more. Okay. That's the idea. And so it's a rational function. And these are two things are both polynomials, right? This is a polynomial. This is also a polynomial. They're kind of ugly because they have fraction or decimal coefficients, but they're polynomials. And so the thing above there does apply. And so the question here says, estimate the maximum photosynthetic rate. In other words, how much photosynthesis could we possibly ever have? Well, this is begging us to look at the infinite limit. Let's see if we had just infinite amounts of light, what would happen to this function?
Can you repeat the question?
In the best conditions. Questions about that? Does this seem okay? What do you think about this? So we're going to look at the limit as I goes to infinity. This is now an application problem. What do you think about the limit as I goes to negative infinity? Does it make sense to look at that? What is that practically saying? If we let I go to negative infinity at this thing, what's that? Thoughts about that?
Yeah, like negative sunlight.
Yeah, like negative sunlight. Like that doesn't even make sense to think about, right? So I just want to point out that we're not going to look at the negative limit because what does it mean to have negative amounts of sunlight? It's like if it's 0, that just means it's dark. There's no light, right? So the negative infinite limit doesn't make sense. Just wanted to clarify that. We're just going to look at the positive limit. Negative light doesn't make sense. Okay. So let's actually answer the question though. So we're going to look at the infinite limit. The limit as I goes to infinity of this function. What do you think? Using the thing above there, which case is this?
You would divide the leading coefficients.
Yeah, so I'm hearing case 3 above there, right? N equals M equals 1 in this case. Because there's a power of 1 in the top and the bottom. Right. There's an I to
Wouldn't
the
that
power
be case
of 1.
1?
Say that again?
Wouldn't that be case 1?
Yeah.
Oh, I'm sorry. Did I say the wrong case? Yep, sorry. That's case 1. Thank you. And so we should divide leading coefficients. Case 1, N equals M equals 1. And so we'll divide the leading coefficients for this. So, all right, I'm going to do my final answer in black. I just wanted to sort of think about this a little bit before we did that. So the limit as I goes to infinity. Feel free to write as much of this down or as little as you want. Try to write enough down where if you aren't like fully following along right now, but you're writing everything down, it would make sense later. That's my goal. You know, the other thing is like on the quiz last Friday, as I was going around looking at people's notes, helping people figure out how to do the quiz, when you don't write down all the stuff in the notes, it makes doing the quizzes harder. And I was trying to like fill in people's notes as they're doing the quiz. The point is you should be writing enough down so that you can get the quiz questions right too. Anyway, sorry, I just started to mention that. Popped into my head. Okay, so we'll divide the leading coefficients. And so that's going to be 1.62 divided by 0.195. Did I get those numbers right? Yes. All right, here we are doing that. And I did this previously, and it's 8.3. And it's got a weird, it's got this weird unit, right? This unit, I forgot to mention that. It's a measurement of light. And so this is like, this weird thing. This is called micromoles. Apparently that's some light measurement. I'm not very familiar with light measurements, but anyway, it's a real function. It has that units. Don't worry too much about that. Just to know that we include the units, right? So the idea is if you are a soybean farmer or whatever, I don't know, maybe you're trying to get rid of soybean. Maybe you have a soybean invasion problem or something. You might care about how much it might grow. And this is sort of an indication of how many micromoles is going to micromoles of photosynthetic rate at the most possible sunlight level. Questions? Maybe I'll just add that note in case people are like, what the heck did we just do? This is the max photosynthetic rate.